Hello everyone, I am Badinath and I am an intern at CERN, and I have been working on one of the projects that I've been working on with Vasil and Wim is how to use C++ from Numba. So most of you must know about PyROOT, and PyROOT has enabled the use of root-based data models in various experiments in Python. And while this has led to people use Python libraries and functionalities, most of these native features of Python, such as loops, are very slow. So people tend to stray away from them. Now, Numba is a package that allows numerically heavy programs to be written in Python without skimming on execution speeds. It translates Python function in basically native code using LLVM compiler framework. And up till now, PyROOT objects were not supported by Numba. This led us to combine both of them and create an extension for PyROOT that enables the use of PyROOT objects inside Numba-cheated functions. So it allows Numba to determine the types of PyROOT objects and efficiently JIT them, converting them into machine code. Let's first go over how Numba really gives us the performance that it gives us. So Python has the flexibility of converting easily between different data types. And this is because each data type that is stored in Python can be represented as a Py object. So let's say you have a statement f is equal to 0.5. So this 0.5 is first converted into a Py object. And this Py object's pointer is what is stored in f. So this process of converting any native value into a Py object is called boxing. And now let's say you want to square the floating point value. You have to convert the Py object back to the native value to do that, and Python calls it unboxing. And once you have unboxed it, you can calculate the square of it and then box it again and store it back into the variable. So these operations are obviously detrimental to the performance, but they are also necessary for the flexibility that Python provides. Now, Numba doesn't do all of this. It simply unboxes the input to a function. It passes the input through the native code that it has generated, and then converts only the output to the Py object. This gets rid of all of the unboxing operations that would have otherwise taken in the function, and it speeds up the operations by a lot. So for this to work, first of all, Numba has to know the type of the input, the output, and the type of the intermediate variables. And once it knows all of this, it can convert the function into native code. But what if Numba doesn't get to know about the types? Then it will spend the same amount of time unboxing and boxing as Python would, and the speed up will be minimal. Let's measure the performance that we get from Numba. So for that, we use a math-heavy function shown below. Here we calculate the tanh of the trace of a matrix and add it back to the matrix. Now, if you see, we have two functions, one that runs in pure Python and one that is jitted with Numba. Now, the only difference is the JIT decorator that we have. And in this, we use no Python is equal to true so that we can instruct Numba to not have any unboxing or boxing operations in it. So if Numba is not able to find any type that it doesn't recognize, it will fail the compilation and not proceed forward. And this decorator is the one that instructs Numba to compile this into machine code. So measuring the execution for this, so we measure it in this way. First, we measure the warm-up time required by Numba. So this warm-up time is what Numba requires for loading modules, compiling the function into machine code, and then running the function. But if once the warm-up is done, Numba is much faster than what the Python function will give us. So this is where Numba is really used. So if you have a function that runs on the same data type for a lot of times, Numba will be able to convert it into machine code, and you will be benefiting from a much faster speed than what Python can run. Now let me introduce you to Cppyy. So Cppyy is an automatic runtime Python C++ bindings generator, and it is used to call C++ from Python and Python from C++. So it's the core of PyROOT, which is why the Numba extension that we designed was originally with Cppyy, and then later ported to PyROOT. And since the extension can be used with Cppyy as well as PyROOT, we will discuss how to do both of them. And you will see it's very similar to use it in both, and you can basically interchange Cppyy for PyROOT when using this extension. So you would say, what do I gain from using this extension? So first of all, Numba makes loops fast. So when you were using Cppyy or PyROOT with Python, the loops with the Python would be very slow as compared to C++. And Numba alleviates this problem, and it can make the loops as fast as C without much code instrumentation. You code completely in Python, so this makes debugging easier. To debug any Numba instrumented code, you just remove the instrumentation line to comment it out, and you are basically now debugging Python code. And if you want to debug Numba code itself, you can use the GTB function in Numba, and it also has a variety of flags that can be used to see tracebacks and intermediate steps that are taken by Numba, and you can find the bug that you are looking for. So this is obviously easier to debug than a code that is set up in Python and uses RDF for hotspots. RDF is root data frame, of course. And we do not have any conversions in the machine code. It converts cleanly, so there is no boxing or unboxing that is required, and we get the maximum speed up that is possible. So the extension also allows both of the worlds of Python and C++ to be closer together. You can easily switch between C++ and Python as and when you want. Moving on to performance comparisons, we use the same function that we used before, and we just replace np.tanh with cppyy.gbl.tanh. So this says that the tanh is in the global scope of the C++, and we want to use that instead of the np.tanh to basically compare the performance. We import the extension first, and then we run this function. Again, we measure the warm-up times. And if you see, it's almost close to the Numba function, the warm-up time. It's slightly lesser because Numba has downloaded all its modules, but it takes the same amount of time to compile the function into machine code. And even the runtime is almost similar, which shows that Cppyy has very less overhead on Numba. Moving on to the features that the extension provides. So first of all, it's extremely plug and play. So you just import the extension, and then you can use any C++ functions inside Numba jitted functions. Let's say here we are using the sqrt from the global scope of the C++, and we can use it to calculate the square root of 4 and pi, and you can send data from Python into C++, obviously. Coming back, we have the second feature that we have is template instantiation. So Cppyy already had a support for template instantiation, and if someone has coded in C++, it's a very important feature to have, because it's used abundantly in code bases, and you cannot use a lot of code bases without supporting template instantiation. So this extensions also works with templates, and as you can see, we have the square function that is templated, and we pass a matrix that is of float type as well as of int type, and it can calculate the square of both of them. Similar to the template instantiation thing, we have overload selection. So let's say you have a function that is overloaded for different data types. Like here we have mul, which returns x into 2 if you are passing in an int, and x into 3 if you're passing in a float. And we again pass the array of floats and ints to see that it is correctly selecting the overload based on the input that is provided to it. Next up, we have the demos. First, we have an example that is directly taken from the Numba examples directory. So here we calculate the Lennard-Jones potential. This is the formula for the same. The epsilon and the sigma that is given here, we assume it to be 1, so that we can, it is easier for us, but you can obviously include it in when you are doing your calculations. Here we have the setup is in C++, so we have a structure of atom, and the data that comes is from C++, which is what usually people have as a setup for their analysis. And here we have two Python functions, one that calculates the Lennard-Jones potential, and the other one which calculates the distance between two atoms. And we have a third, these two are number jittered. We have a third which uh, sends in the individual atoms to the functions and the distance. And this one, if you see in the Numba examples, it is jitted, but in our case, we haven't jitted it because currently the jitting doesn't work with vectors, but we are working on it and we will add that support soon. So as you can see, we can calculate the potential, but of course, this potential doesn't mean much because the values are really arbitrary. So, but this only proves that we can carry out analysis in this form. Next up, we use the extension with PyROOT. So we again have to import cppy.numpy extension for PyROOT. Also, we use the T-Lawrence vector class from root. It has four properties, the momentum in the 3 dimensions and energy. It also provides transverse momentum that it calculates on its own, but even users can calculate it by using this formula. And we use this formula to calculate it on the Python side, and then we compare against the PT that we get from C++ to show that the accuracy of the calculation remains the same. So we basically create a vector of T-Lawrence vector and fill it up with random values. And now we have two functions, actually two pipelines. One pipeline uses pure Python to calculate the PT, and the other one uses number jittered function to calculate the PT. The first, these are feeder function that again feed the T-Lawrence vector to the function so that it can calculate the PT. And again, as done before, we calculate the warm-up time and the elapsed time. So here the warm-up time is significantly less because the function that we are jitting is very small. And as you can see, for pure Python, we take about 0.007 seconds, whereas for Numba, we take about 21x, we are 21x faster for it. And I've also printed out 3 sample values to compare visually, but since there are a lot of other values, I have used a computationally method to compare them. And as you can see, all values indeed match. So showing that we are accurate both in Python as well as C++. Moving on to RDF, you can also use this in RDF using root number declare. So root number declare was introduced so that Python can be used inside RDF. And now you can use PyROOT inside the Python that is used for RDF. And it comes a whole circle. Here we just show some sample values such as 2 to the power of 3, 4 to the power of 5. And we also pass an RDF through a power function. And as you can see, it gives you the all elements to the power of 3 as it should. Now, finally, I would like to talk about the future work that we want to achieve. So first goal that we want to achieve is to have complete C++ feature support. Currently, the Numba extension only allows us to work with PyROOT functions that return primitive values. We are actively working towards supporting returning of complex objects and reference types. Along with this, we also want to support memory management, constructor support, and virtual inheritance. The second goal that we have is called inlining. So for the code that you saw in calculate PT, we have two calls to px and py. And in C++, this would be optimized away by doing memory access. So we access the variable of LV directly instead of calling functions from it. And that is what we want to do at the machine code level as well using Numba. The third goal is to support GPUs. Numba already supports CUDA GPUs, but it doesn't support PyROOT objects right now. And we want to support GPUs also in the future. And finally, we want to support automatic parallelization. So OpenMP has these instruction at the machine code level that can be inserted automatically to parallelize the computation. The user just has to specify if he or she wants to parallelize it or not. Finally, to conclude, I would like to say this extension enables use to use PyROOT with Numba. This gives physicists a different way to carry out their analysis. For loops are not to be seen as something that is very slow anymore, and it is very easy to use. You can just import cppyy.numba to use C++ in Numba. It makes Python code faster while keeping debugging easy. So all debugging features that are available to Numba users, which are a lot, are still available, and with the extension enabled, and it makes it easy for users to debug Numba code. So how do you use it? So currently the PR for the PyROOT extension is open and will soon be merged into root master. Until then, you can try out the notebook in the repo that I have created for PyHEP. It is also linked to the timetable. That's all from my side. Thank you.
Thanks so much, Bhagyananth. That was really interesting. So we have some minutes for questions. If people have any. There aren't any in Slido at the moment. Guess you can. Oh, yeah, okay. Jim has asked one. He's wondering, how is this related to efforts to include Numba in our data frame?
Yeah, this is also related to that because I mean, our data frame already uses Numba in the sense that this Numba declare function uses call func in Numba to call to make this Python function into a C function, and then you are basically calling a C function that is created from Python function here. So I guess it's like a full cycle now. You just you can use C++ inside the inside the Python function, and then it will get converted into a C function using Numba declare.
Okay, but this is a separate implementation. This is these are two ways of going about it that do slightly different things, right? It's not that one.
Which, I mean, I'm not sure which one you're referring to, so if you can explain that.
Like the root Numba declare that's using a Numba function in our data frame. What you've developed here is distinct from that. That was my
yes,
question.
It is distinct from that, but it also, so this is also one of the goals that like whatever we can use in like if we whatever we are using in Numba will be automatically be supported by this, because this is also cfunc related. So it's I'm not sure exactly what you are looking for in Numba with RDF. If you can tell me that, I'll tell you, but this is basically is the efforts that are going into it.
Okay, thanks. That's an interesting discussion there. And Eduardo, do you want to ask?
Yeah, quick question. My usual question: are you discussing or in touch with any say physicist analysts to see how this is attractive for them, or how they would use it? What would be in practice the benefits and stuff like that? Or this is for the moment purely, say, quote unquote mechanical work?
I mean, it is a bit mechanical. We are trying to release it in PyROOT. It is already released in Cppyy, so people can try it out. And once they try it out, they can. I mean, that's why I think I'm also presenting it here, so that people can know about it. They can try it out and give us more ways that they want it to evolve.
Of course. Okay. Thank you.
Yeah, that's very interesting, and I hope that people take you up on that, potential users can have a look at it and feedback to you how much they like it and what improvements might need to be made as well to make it as useful as possible.
Yes.
I don't see any other questions, so thank you very much.